Hi, so this video will show you how to measure current using an Arduino and the ACS712 sensor. It feels straightforward to begin with, and you get pretty good reading comparing to, let's say, a multimeter. But there is much more to it than that, which is why this video is not quite as short as you might expect. Now, before we get to how, let's start with why. Now, why would you need to measure current in the first place? Let's say you want to be charging an 18650 and you want to see how much current you're sending to that battery and how much you're getting out. Or you might want to build the entire BMS, battery management system, and see how well that is working. You might be looking at charging LFP battery as well, or one of these like standard 12-volt ones. You might want to use a solar panel to charge one of your batteries, or might have like an LED strip and you want to see how much current it's consuming or how much current it's consuming as you dim or increase the brightness. So yeah, all of these things are possible so long as you know how to measure current. So ACS sensors, they come in three varieties. The 5 amps, 20 amps, and 30 amps. Now, can you tell which one of them is which? Doesn't seem to be any markings on them. What if you turn it upside down? Nope. What about this way? Nope. Sideways? Nope. There's no real way to tell. What about from packaging? Again, you can't tell what type they are. So what can you do? You can, of course, unpack them. Have a look inside. No way to figure out. So where do we start? I'm afraid you're going to have to start with a microscope. Now these ACS modules come in three varieties. You have your 30A for 30 amps. You have your 20A for 20 amps. And you have 5B for 5 amps. Why 5B instead of 5A? I don't know what's the logic in that, but yeah, just the way it works. So you have 30, 20, and 5. Once you went through the process of checking your ACS modules to find out which one is which, it's always useful to label them. So what you get is, this one is 5 amp, this one is 20 amp, and this one is 30 amp. And then I don't have to go and check any of that with the microscope again. Well, it's useful if you're using different types or if you have different types around your workshop and you don't want to get mixed up in the future. So let's take this simple circuit as an example. We have a power source, which is our power bank, and LED strip as our load. And once they're connected, current can go round and round in circles. And that means it generates a magnetic field that can be measured with a sensor such as an ACS. All we need to do is to connect it in series, so that the current still goes through our sensor without being interrupted in any way. In this case, it's connected to Arduino already, just to show you how the full setup will work. And let's say, yeah, we get the power flowing from here through the current sensor, and calculations for the current strength end up being within the Arduino. And that's how it works overall. Just at a very high level, not much more to it. So this is a very simple illustration of how it can be wired up. And yeah, let's see that in action. Before we actually go ahead with wiring everything up, let's have a closer look at this breakout board for this ACS712 chip. You can see the 3 pins for Arduino. There's not much on the back, just a label that actually says what board it is. It's actually the name of the chip and the breakout board at the same time. And you can see that, yeah, it has these pins for the screw terminals, and that's to connect your load. So let's have a closer look on the whole thing under the microscope. You can see the screw terminals, are pretty straightforward. You can connect it with a screw, and you can see the actual chip connection as well. Now let's look at the rest of the board. We have the 2 capacitors for smoothing out the signal. We have the resistor and the LED, which is power LED, and it comes on whenever we have the power connected to this board. We have obviously the 3 pins to connect the board to the microcontroller. We have the ground and the VCC, and we have the out, which is where we read the signal. So yeah, seems pretty straightforward. Let's carry on and see how we can actually wire this up. An important part is to get the wiring done correctly. So we need VCC as in power. So we connect the 5 volts of the Arduino into the VCC pin, just route a wire around that way. We need to collect ground to ground. There are 2 ground outputs on this side. You can choose either one of them, doesn't make a difference. And of course, we need to get the signal out of the ACS module back into Arduino. So we need to connect the out pin into the any one of the A pins, like A0 to A5, doesn't matter which one. And once ACS is connected to Arduino, you have to make sure that the load is connected in series against these 2 screw terminals. And then the whole thing should work. You can wire up the ground and the VCC first, just to see if the chip is actually working and everything is working as expected. So you can see LED light comes on, which is a good sign. That means this board is getting the power from the Arduino. And even before you have the signal connected, you can confirm that it actually works. At least that part does. Now there is a slight problem. Let's say we have this USB power bank, right? Arduino 1, USB. And how do we get inside the USB signal? So do we get the wires connected to it? And yep, let's connect it up. And then the other wire is, also USB. So what do we do? So in the olden days, what we would have to do is cut into USB cables. So you see this will be USB cable, and you'll cut into just the side of it, and then connect your wires, so you get the positive and negative extracted, and this way you can measure things going through USB. Same with the blue data cables. You can do something similar. You'll basically get a USB cut into, and this is useful to an extent, but there are better ways, and a potential better way will be using something like this. So this is effectively a USB breakout. You get a USB cable from one side, and you get the wiring of several wires that you can put here. But here's another way. Here. So what you get is USB, well, what is now the old USB, one male, one female, and then you get all the wirings that you can do in between, so you can have even additional wires to monitor your positive and negative, and effectively get to hack inside your USB signal if you need to, and inside your USB power. So you can this way connect anything from one side to the other, and it will work without any issues, while you allowing you to monitor either the voltage or current, or in fact both. Let's say you have a power bank, something like this. This one kind of fully opened, but it's still a power bank that works. And you want to connect a cable to it, which you can. There you go. USB cable works like this, right? But you want to find out how much the energy is flowing, how much current is flowing. So what you can do is connect up, actually the wrong way around, this one. Connect this cable in between, and then you drag this out, and you can connect these two together. Right. So what you end up with is the same as before. You have your cables together, but this way you can fully monitor what goes inside. So what we can do with this setup, the simplest thing that we can do is to measure the current flowing through an LED strip. Something like this. Yep, that will do. So this is USB compatible. Yeah, that's good. We're able to connect it up like this. Right. And now we can use a clamp meter. We can take a negative, actually can take either one of them, clamp it, and put it like this. Just so we don't get too much glare, let me just rotate that a bit. Yep, there you go. Right, so we can see that it's showing -2 at the moment. That doesn't mean much. Basically, it's just getting no reading at all. So it's not 200 microamps in negative. It's just nothing. Because at the moment, there's no current flowing. So what we can easily do, just switch on the power bank. And you can see we're getting negative 1.7 amps, which basically means it is amps going in the opposite direction of what we expect. We can switch that off. And let's clamp a positive cable instead. Positive lead here. The back. Again, avoid the glare. Avoid the glare. And let's try that again. Right, so now we're getting 1.1 amp coming out from the power bank through the cable, detecting the current from through here all the way back into these lights. And yep, that does work. We can do the same with our ACSs at some point. That should work even better. But this shows a general principle. The whole USB breakout board makes the whole thing a lot easier. You don't have to cut any wires. You don't have to mess with either your power source or your load. You can simply put the wires in between and then measure them with a clamp meter. And you can even find out the voltage as well. Let's say now we want to measure the same thing, but with an ACS. This one is 5 amps. And we want to put that within this chain, much the same way, so we can find out how that works. So let's do that. We'll need to flip this. We can actually disconnect this part, makes it easier. We'll need one of the tiny screwdrivers that we get with this thing. Yeah, here's one. Right, we can disconnect this positive wire. And we can connect it up to one of the leads here. Yeah, it should work. Might actually be useful to unscrew it a bit. Unscrew it even more. Yeah. There we go. So we effectively connect it in series, and we'll put in its place wherever there was this positive, should be right here. You put this small cable as well. Small wire rather. Yep, it's in there. And we're going to screw it back in as well. Oh, that didn't work. Try that again. Yeah, we're getting there. Fine. It's connected. And now we connect this back to this one. Fine. It's a bit fiddly, but we'll get there. Yep, it works now. Right, so we have positive coming through all the way to the other side. So hopefully we didn't break anything in the process. So let's flip this over and switch it on again. I can actually put that back. Get this out of the way. Well, let's try. Yep, still works. Power still flowing. So all we need to do is now connect our Arduino to these pins, and I should be able to monitor the current that's flowing through as well. Now, how do we wire up Arduino to connect to this ACS? We can use the same Arduino Uno that we had before. So as you can see, it needs two things, so on 3 cables. So it needs power. So it needs VCC and ground, which should be 5 volt, and then the third pin in the middle is for actual signal. So power is pretty straightforward. We get 2 cables, it's male to female. So we get this one for ground and this one for VCC. And we connect them to Arduino ground. Has more than one, doesn't matter. And we get 5 volts as well. Make sure to get the right bit. Right, so that part is done. We just need a signal cable, which works exactly the same way. We connect our signal. Shouldn't do that last because it's now fiddly. And we can choose any of our ADC pins here from 0 to 5. Let's just go with a pin 0, A0. And that's our wiring done. So basically the sensor will be getting the power from us and the ground as reference. And then we'll be getting back the signal that it generates back to us. So yeah, we'll be able to measure it on the Arduino side. Pretty straightforward. All we need to do now is upload the code and, of course, connect our Arduino with the USB cable. And we should be good to go. We should be able to actually measure the current directly. And now comes the fun part, of course. Let's see some code. Let's go through it sequentially, of course. And we start by defining the sensor midpoint, which is 2.5, and it's always 2.5 for this type of chip. And let's specify the volts per amp. Now, why is it 2.5 and why is it 0.185? Unfortunately, we have to have a look at Datasheet to be able to figure that out. So here's a graph of the output voltage for a specific current level. And this one is for the 5 amp variant of the ACS712 chip. And what we can see here that the current can be obviously positive up to 5 amps here at the bottom and negative all the way down to minus 5 amps if current is going in the other direction. And for that, we get a voltage reading between 1.5 volts and 3.5 volts. So we should never get anything below 1.5 volts, even if we get a much lower, even if the current is stronger and negative, and we should never get anything above 3.5. Now this would mean that we have 1 volt up and 1 volt down from the midpoint. And if we multiply the 0.185 by the 5 amps that we can measure, we magically get this 0.925 a number, so that actually is roughly 1 volt. So this pretty much explains the limitation of this chip, specifically for this 5A. So we get this 1 volt that we can measure, and we have to map that somehow to the 5 amps in either direction. And the 0.185 is the millivolts per amp figure that we're getting from the datasheet right here. This obviously is converted to volt. And as you can see, for the 20A variant is 100, and for the 30A variant, it is 66. So now going back to our code, you can see these values written here in the comment. So we're using the 5A variant, and so that's why 0.185. And we also have the 100 millivolts for the 20A variant and 66 millivolts for the 30A. So if you switch into either one of them, you can just copy paste them from the comments. Yep. So let's move on with the rest of the code. The setup part is pretty straightforward. We begin the serial and set the baud rate to 9600, just so that we can then read the serial output and sort of see the logs and the graph of our data. And then we set the pin mode to input for A0, because in this case, we're going to be reading from that pin. That's pretty much it. If you're using different pin, obviously specify a different value in there as well. The next line is pretty self-explanatory. We just analog read from the same pin to read the sensor value. And then we convert the analog value that we got from the sensor into a voltage value. Now, exactly why do we have to do something like this? Now, an Arduino ADC, or analog digital converter, the bit that we're actually using to measure this voltage, is able to read anything from 0 to positive 5 volts and then convert that into a digital output, which in this case a number between 0 and 1023. So that's why these values, sort of real life voltage representation, come into our code, come into our program as a number between 0 and 23, and we know that that represents a voltage between 0 and 5. So then to convert the same digital value between 0 and 23 back to 0 to 5 volts, we use this map function. Well, we use the fmap, which is the floating point version of the same function that Arduino has. And yeah, we just specify it the range 0 to 1023 and 0 to 5 volts, and it works every time. That's it. Now this line for converting the ADC value to voltage is exactly the same as the line above, or rather it will have exactly the same effect. We just prefer to use this function just because it's more generic and it's clearer at the first glance exactly what it's doing. And it's also more usable for other applications, sort of other ADC readers, not just the built-in one from Arduino. So if you prefer, you can use this line, but we're just going to get rid of it to keep things a bit more simple. Now, because the sensor produces voltage values relative to the midpoint, we subtract the voltage that we got from our reading from the 2.5 midpoint, and then we divide the whole thing by our volts per amp value, and then we get the actual current value. These lines then print the sensor value, the voltage value, and the current in a nice format that then can be automatically interpreted by a serial plotter, so you can see the whole thing on a graph. You can delete all of that once you're happy with how it works. It's just for sort of debugging and demonstration purposes. And here we set the delay for 500 milliseconds or half a second. So that means we would measure a current just once every half a second. That's pretty much it. The fmap function here is the floating point equivalent of the map function that's already there as part of the Arduino sort of framework. I can see a lot of examples online of people just using the map function when working with floats. And if you actually use that, it will give you incorrect values. So please make sure to use this version of the map that works specifically with the float numbers. And then, yeah, that's what we use in this case, and it works just fine. Let's upload this code and see what we get. So we go to upload. It's compiling, it's uploading. And yeah, we're done. So let's have a look at the serial plotter. Right, immediately we can see the current value, the sensor value, and the voltage value because of the way we printed them here in this nice format. So because the sensor value is so high, the scale kind of doesn't let you see anything else here. So let's hide the sensor value. You can actually see the current, the voltage value and the current right here. So current is basically 0, and the voltage value is 2.5, which is the midpoint. So let's try switching on some lights. Yep, you can see that immediately the voltage value drops, which means we minus a smaller number from the midpoint, and the current value goes up to a sort of 2.8 area. So we can, yeah, switch off the light, and it goes back. Yeah, the voltage we read is 2.5, and the current we read is 0. And we can just hide the voltage value and just see where the current is currently at 0, lights on, and it's at 1.28 amps roughly. And it's a bit unstable at the moment, but we'll get to multisampling and more stabilizing of our reading later on. Let's see our entire setup in action. So we get Arduino finally connected, and we have the clamp meter connected and all sort of clamping the positive wire. We get the SCS in between, all connected to a power bank that then goes to the all the way here to the LED strip, which is sort of wound in there. So we get a low value on the clamp meter, and we're getting also crazy low values in our a serial plotter within our Arduino IDE. So let's see what happens when we actually start sending some current. As you can see, it goes up here. It's going to gradually climb up to 1 amp. And similar happens on our serial plotter. As you can see, our ACS sensor detects the current flow, sends that to Arduino, and then gets translated to voltage, and that gets converted into current calculation. And we can see it's floating around 1.4. So it shows that we get 1.4 amps coming through. And this may or may not be correct. I mean, it is much higher value than what we get on a clamp meter. So let's switch that off. You can see it's all dropping closer to 0 on both the clamp meter and inside Arduino's serial plotter. So let's switch it back on once more. And it goes up again. Yeah, so there is a discrepancy between the values, and it'll be good to figure out exactly why. So yeah, we'll get into that. So the LED strip that we have here gives us only a constant current. It sort of usually floats around 1 amp, a bit lower at the moment for some reason, but we can try something like this, which is also an LED light. Should work more or less the same way. Also USB powered. Slight difference though. We can control how bright those lights are, which means we can control it from lower current level to high current level and see how that translates into a measurement. So let's try that. So we have switched to another light. So this is the LED strip is completely disconnected. And now we connect it to the LED light, which is here. So first thing first, we switch on the power bank. Nothing happens because the light is actually not on, but you can see that the little light came from here. The current flow is so tiny that it's not really measurable. So let's switch it on. You can see some of the brightness, and the current goes up. So this is measured as 0.7 here, and it's measured much higher inside our Arduino. So let's make it a bit dimmer. Let's reduce the brightness. Goes all the way down. This is minimum. It's hard for it actually to detect the level of current. It's very close to 0. It goes into milliamps, I guess, because these are LEDs after all. So let's increase it back up. So our clamp meter shows gradually increasing current. And the same goes for our Arduino IDE, rather, serial plotter. Shows us on the graph that the current is going up. Increase it a bit more. Get one up to maximum, so it's close to 1 amp. And it's showing still 1.4 on our current serial plotter, while it's showing 0.7 on our clamp meter. Our clamp meter goes up to 200 amps, which is why most likely it's not so great at measuring something this close to 1 amp. So yeah, it's hard to say which one of them is more correct here. Now, you might say that the discrepancy we get between the clamp meter and what we're reading with ACS is not that high, and we can live with that. Well, we would not be too happy with that. We either need to know which one of them is more accurate, or if ACS is generally good enough as a measuring sensor. So we need to trace the source of discrepancy, and we'll have to try to introduce another multimeter, this cheaper one, but still should be able to work with that. And yeah, we'll need to see what value does it show. And if that still doesn't answer the question, we'll try a third multimeter until we find out which one of them is right. Let's see how that goes. So what we'll need to do is to completely disconnect this cable and to connect the multimeter, the new one, in series with these cables to see how that goes. So basically replace this wire with a multimeter inside. So let's switch off the lights. And we need to unscrew this. Actually, it might be easier to just unscrew this part and replace this relatively short wire with a whole multimeter. Yeah, why not? Okay, so we can connect the positive here. Let's unscrew that a bit more. Yeah, more or less. Should be close enough for the small current. Yep, no, that didn't hold. One sec. Let's unscrew it even more. To the max. Twist the cable. Yep, it's now properly inside. You just need to secure it. volts. And that's the positive cable from the multimeter. And we also have, of course, the negative. So let's connect that here. We can leave the yellow cable in. Just put that out of the way. Okay, we can remove that. Twist the cable. Put that in its place. And secure it once again. Yeah, so now we have this very complicated setup of an extra multimeter inside. Not at all confusing. Just put this on top of our power bank. And let's switch on the light. It's on already. Let's switch it on. So you actually can detect current, which is a great start. So actually we can see straight away that this multimeter shows a higher value, and it actually much closer what we get in our Arduino. Actually we get 1.2, around 1.2 amps there. So this much cheaper multimeter is better at looking at a much lower range of amperes, so it goes to milliamps, while this clamp meter, it doesn't kind of look at that. It goes to 200 amps and 1000 amps. So that's why for both AC and DC. So it would be, not quite appropriate for measuring something with such a small ampere range. You actually can put it into 200 milliamp mode and 20 milliamp mode. But all it really does is, doesn't do much else. This was quite a useful exercise after all, because it shows us where discrepancy lies, that our ACS measurement is much more accurate than we thought. Well, the fact that it does not match this clamp meter doesn't mean all that much, because the clamp meter is set to 200 amps range. It can measure 200 amps and 1000 amps, but it's not great, I guess, at measuring lower amp values. Well, this much cheaper multimeter is able to measure microamps and milliamps and so on. So it will be much better at this range. So you can see it matches much closer what we get in Arduino. It's 1.2 here and 1.2 on ACS. And as we actually dim the lights a bit, you can see it's dropping here to 0.8, and it's close to 0.8 inside Arduino serial plotter as well. So we can actually remove some of that discrepancy by averaging. So what multimeters do, they take multiple samples and then they average them out. And we can, in fact, address that right away and change our code to have some sampling involved as well. Let's try that. So how can we read current with Arduino and using multisampling? We add this kind of function, which we'll go through in a bit, exactly how it works. And we're simply replacing the direct reading of analog values with reading this with multisampling, like this. So we specify the same pin and just the sample size, in this case of 20, and the rest of the code will work the same. So let's have a look at what this function does. So we added some comments around this function to briefly explain what it does, and of course all this code is available on our GitHub. So we specify whichever pin we like to read from. So in Arduino Uno, it is anything from A0 to A5. We specify the sample size. It's 20 in our case. It can be 200, maybe even 1,000, depending on your use case. But do bear in mind that there is a sort of 3 millisecond delay in between each read, just to make sure your actual read function doesn't take a very long time. So it basically gets the average value. That's all it does. So for every number in the sample size, let's say it's 20 in our case, it will read the value 20 times from the same analog pin. It will add them all up here to the total, and then it will divide by the sample size at the end to get the actual sensor value. It is really useful and smoothing out the volatile sensor readings, and it gives you a much better value, much closer always to multimeters, because multimeters do averaging. And yeah, it's very useful for both voltage measurement and for any other signal reading. So yeah, this is a very useful function for a lot of other projects. And that's all it does, just getting an average, that's all. Because our multi-sampling reads will take more time because of this delay, let's reduce the overall delay that we do here to, let's say, 100 milliseconds. And we still be reading roughly every half a second, but just, yeah, this whole reading process takes longer than it did before. And if you want to simplify your code even more, you can use this function. You can just have your read voltage with multi-sampling right away. And let's use that instead. So instead of us reading the sensor value and then converting it, we can just do like this. So this again will be a 0 and the sample size 20. And we can get rid all of this. Yep. And then we can't print sensor value anymore because it no longer exists. And this becomes our code. Pretty straightforward. And this function is reusable for a lot of other applications as well. So as you can see, the reading we get inside Arduino IDE that we get from ACS all the way through as a calculation to a serial plotter, it is a lot more volatile. It is sort of around the same 0.8 area, but it jumps around up and down. Multimeters, they do some averaging on their side as part of their calculations. They take multiple samples and they average it out. So if we want to match it closer to this relatively cheap multimeter, we have to do the same on our side. By the way, the fact that it's negative here doesn't really mean much, just because of the way we connected the wires. So if we switch the negative and positive here, we're going to get positive value in terms of amperes here, but that's all that there is. So let's deploy the code that will actually do some multi-sampling. In this case, we'll just do sample size of 20. So should be relatively quick in terms of sampling and calculations, but let's see the effect that we'll get. And pretty quickly, we see that the values we get is stabilizing now around this 0.8 level. They go up and down a bit, but not nowhere near as much as they used to be in this volatile, spiky area here. So let's try to do a sample size of, well, let's do double the size. Let's do triple size. Let's do 60. Just to see what that will do. So it starts to look a bit more volatile here even before we upload it, but that's just because the scale of the chart changed. So now we at 60 sample size, and yeah, we're still floating around this 0.8, 0.82 mark, as we have here. That the current does change slightly. You can see it's even changing a bit on this multimeter, and yeah, it's much more accurate. The measurement takes a bit longer, but the values are much more stable. Even though they're moving on this chart, you can see the range is much smaller. We're much closer to 0.8. There was just weird spikes here. Let's go back to the sample size of 20. It was better. So the keyboard disconnected, it's uploading. So let's actually remove this delay of 1,000. Let's make it more 100. And let's make a sample size of 200. We're disconnected. The code is re-uploading. And what do we get? Yeah, the value is changing a lot more frequently because we now don't wait for a second in between measurements. So we're getting values much more constantly, and yeah, and it's much more stable. Get sample size of 200 with a 3 millisecond sleep in between, so it takes us some time to measure. So you can see the actual range has decreased even more here on the chart. So we are much more stable around this 0.82 level. So now let's go dim it a bit more. Oops. So we drop to 6.7 on the multimeter. And yeah, we drop into roughly the same level inside of our serial plotter as well. And as you can see, this multimeter just shows 0.1, which is not very helpful at all. So let's increase to the max. Yep, so we have 1.2, and we add 1.2 on our serial plot as well. So it works. So just, yeah, not a good source to compare it to. Let's get rid of that. Yeah, so just for our own sanity, cleaned up all of the setup, removed the clamp meter because it wasn't really all that helpful and was not showing us good enough reading. And as you can see now, also reversed the cables, so you're getting a negative here and starting with a positive here from the multimeter, and we're getting a positive ampere reading instead of negative one. And yeah, the values seem to correspond very closely. You're getting pretty much the same value inside our serial plotter than we do here. We can try to switch to a microamps range. Doesn't seem to make all that much difference. So we're going to go back to where we were. So yeah, this ACS sensor seems to measure it more or less exactly the same way as this multimeter, and definitely much more accurately than the clamp meter that we had. Let me just bring it up here. So it is better than this, at least, which is always a good start. Now, the main reason that we're interested in measuring current is to use the solar panel cells to then drive our DC to DC converter and then charge batteries, power banks. So yeah, videos for that should be coming up shortly.